Swayam Prabha. Digital India. Educated India.
For today, it doesn't matter. I don't want to make that big a distinction. And the idea is that you want to parallelize programs that have dependencies. Typically, you're talking about programs with nested loops. The easiest way of parallelizing loops is the lucky, fortunate situation when the loop iterations are independent. If that is the case, then you just mark one of those loops with a for all or with a pragma, and you get parallelization. This may not necessarily be the best parallelization because in reality you have to temper locality and many other things that you have seen through the course of the week. Okay. What I want to do today is to give you this overview of the main steps when you want to take such a loop and you want to parallelize it using the polyhedral model or using polyhedral compilation. And the specific topics that I want to cover in this session, and again, this is part of material that I normally teach in a class to seniors, and it covers typically 2 weeks of 1.5 hour lectures. So I may go fast if you like, I may slow down if you like, you just let me know. Okay. The main steps are what is called dependence analysis, and that is really where some of the key polyhedral techniques come in, and a seminal series of papers by Paul Fautrier in France are relevant. Then I will talk about fine-grained wavefronts, which is basically how you actually choose the parallelization. This is actually a fairly deep and complicated problem, but I won't go into it today or in this overview because it's a fairly deep and complicated problem, and what I want to do in this is to work more with examples. And when we work with examples, you will see that the parallelization, the orientation of the wavefront and all that is going to be relatively easy for you to see and to see intuitively. Then I will talk about how the program is transformed, and that actually turns out to be an interesting thing. Then I will tell you what I didn't talk about. Okay? All right. So you have seen all these things in some other context about dependencies between statements. If you have two statements, let's call them X and Y, where X executes after Y in the sequential version of the program, X depends on Y if they both access the same memory location and one of them is a write. Okay, so technically you can classify all four of the kinds of accesses: reads, writes, pairwise, and if you read after a write, that is called a true dependence, and that is basically that the second instruction is reading the value that the previous instruction produced. Others, as you will see, are related to the memory artifact of the program. They're not really true dependencies. Okay, and you've seen this. So what changes when you want to do so when you want to parallelize, when you have a true anti or output dependency in the program, that order cannot be changed when you parallelize, right? Any thoughts on why? See, I really would appreciate if this is more interactive. I don't want to, I'm seeing a screen. I'm not even seeing your faces on in the meet. So really, please try to be interactive. And if you have comments in the chat box, and Rama can let me know that there are questions. Okay. So any thoughts on why
It would change the correctness of the program, I think, if
you
we
change
change
the
the.
correctness of the program? Exactly. You change the semantics of the program, and therefore you would be computing something that is different from what the program originally computed, right? So this is not legal. A compiler that does this will be the laughingstock of all compilers, right? Okay, so what happens in loops? Well, you have a statement, if you think of it as something that has a label in your code. There are many instances of the statements. And there are many elements in the data, because the data is typically a multidimensional tensor. Okay, so you're accessing within loops arrays or multidimensional tensors, and so there are multiple instances and multiple elements. And so what you have to do is to take this problem of dependence analysis to identify which statements are independent and which statements are not. That problem becomes more complicated. Okay, and we are starting with this simple case that in the original program, none of the loop iterations may be independent. Okay, so let's take a look at a few simple examples. Right, so you have a set for I equals 1 to n minus 1, j equals 1 to m, and those loop bounds are the same for all the three examples. Okay, the loop body is what is different in each of these. Okay, in the first one, the statement is updates an array variable a indexed by I and j. In the second one, it indexes an array variable b indexed only by j, and c in the third example is a one-dimensional array indexed by I. Okay. All right. And when I said in the previous slide that there are many instances of statements and there are many elements of data, what does that mean? It means that once you have a program like this, what you have are what are called iteration spaces and data spaces. Right? This is basically identifying a set that tells you what is the set of statement instances. Okay, and in our examples, the set of statement instances is a range of values for the indices I and j. You have some lower bounds and you have some upper bounds. Okay, they all happen to be linear inequalities or affine inequalities involving the indices I and j, and maybe some size parameters like n and m. Okay, so when you have linear inequalities, the first thing that comes to your mind is, oh, I have something that is the intersection of half spaces or something like that. You go back and rethink about your linear algebra background, or if you have some optimization background, you may think of linear programming background, and it's like the feasible space of a linear programming problem. So that is the iteration space, the intersection of a set of half spaces, and that's a polyhedron. Okay, so let's look at what the iteration space of our example looks like. Our three examples for I equals 1 to n minus 1 and j equals 1 to m minus 1 is basically a rectangular region whose corners are 1, 1, and n minus 1, m minus 1. You all buy that?
Yes.
Okay. Now the data space, again, remember I was talking about instance-wise and element-wise. So the data space is the set of values of array indices accessed, array or tensor indices accessed by the statements in the program. Okay. So in example 1, if you notice, the A is a two-dimensional array and it is indexed by I and j. Right? So the data space is identical to the iteration space here. Am I right or am I wrong? It's a gotcha.
Right. Right.
I am not right. I'm pulling the wool over your eyes. Remember
One
what?
point is missing.
What is missing?
N minus 1 comma M minus 1 is missing.
N minus 1, M minus 1 is not missing. If you see, those are the corners, and at every point on the left hand side, I see Aij, right? But I also see some axes like on the right hand side, which is Aij minus 1 and I minus 1j for the second reference, okay? So it's the data space is nearly identical to the iteration space, but there are some special points that are accessed that are outside the iteration space. On the left, it is, or no, on the left and right, it is extended by plus or minus 1, and vertically it is extended by plus or minus 1. So it's like a very, very fat cross with, with the square in the middle being the majority of this, right? Extended vertically by 1 up and down, and extended horizontally up and down by 1. Okay. Now, is that a polyhedron? See, if I draw a picture, let me share my other screen. If I draw a picture, here is my I-axis and here is my J-axis. Okay. And my iteration space is all the way.
We can't see the picture.
You cannot see the picture because I haven't stopped sharing. You're right. Thank you very much. And I have to start sharing the right thing. I think this going back and forth is going to be a little painful. Where is my... let me share a window. Okay. Are you seeing my my tablet?
Yes, sir.
Yes.
Yes.
So this is the I-axis, this is the J-axis. Okay. This is 1, 1. This is I equals N minus 1, M minus 1. Okay. And I am accessing, if you remember, A of Ij on the left-hand side, A of I minus 1j on the right-hand side, and Ij minus 1, right? So my data space, actually, I realized why there was no response. There was a mistake. Okay. I am accessing all the points here and all the points here. Okay. And I am not accessing these points, right? So I'm taking the original square, which was not original rectangle, and I'm shifting it up by 1, and I'm shifting it left by 1. That means the last elements in the row and column are not being accessed, right? So is this set, which is now my, if I draw this like a caricature, it's going to be basically this shifted right, shifted left, right? Oh, sorry, shifted up and shifted left. Okay. That plus the original, because on the left-hand side, I am accessing Aij. Is that a polyhedron? What is your intuition? And it's okay if if your intuition is wrong.
It is a polyhedron.
It's nearly a polyhedron, but look at this point in the corner. The top left point 0, 0 is not in the polyhedron. So you can construct a polyhedron that contains exactly those points. But the better way to think about it is that it is the union of polyhedra. It is the union of the original square, the shifted up square rectangle, and the shifted left rectangle. So at least if it's not a single polyhedron, it is the union of number of polyhedra. a finite number of polyhedra. Okay? So, in example 2, what is the iteration space and what is the, well, the iteration space we've completed. What is the data space? Let me show you the, my machine is now slow. What is happening? I apologize, I'm sorry.